5 is very important. It's difficult. It is more difficult than what we've been doing so far because we are going to be undoing chain rules, okay? So for undoing chain rules, let's think about how a chain rule worked. We would take the function's derivative, leave the stuff there, but have to multiply by the derivative of the stuff. So now we have to try to find the derivative of the stuff. Is it sitting in the problem somehow that I can undo this process? So substitution, I really need you to pay attention and follow along with me and work on these because it is a difficult section and I want to make sure you guys understand it. We're going to be taking the rest of the week and working on 5.5 for the remainder of the week so that we just make sure we try to get this stuff. So let's look at how it works. If we have a function with a function inside and we see its derivative on the outside, the way that we're going to do it is we are going to think about the fact we're going to let u equal the function inside so that du dx will be the derivative of the function inside. So what we get is we can get this dx and g prime of x out of the problem. We can get this out of the problem and make it a much simpler thing. So if you identify the inside function, what is the function that's locked inside? What is its derivative on the outside? This process is not hard, but it's a matter of undoing our chain rules. So we have to figure out what's the function locked inside of something, and then is its derivative or a multiple of its derivative living in the problem. So that's what the substitution process is going to entail. So that's where we're heading with this stuff, okay? Just follow along, yeah. Maybe if you want to write it down on paper or something, you can. Okay, so what the chain rule does, if you recall, the chain rule, we take the derivative of the outer stuff stays there, the derivative's on the inside. Remember, an integral is going backwards. So to go backwards, we need to discover what the outer function is and what is the inner function. So you'll see that these things flip-flop locations. Was there anything there to write down? Okay. So here's the strategy you want to take. There are 5 steps when you're doing these problems. The first step, what is the function? The stuff that is stuck, and what is its derivative? 2, we're going to let u equal that stuff. We're going to let du equal the derivative of that stuff. We're going to substitute in so that all of the original variables become u's. We're going to integrate that more easy problem. And then to solve, you have to put the original variable back. Okay, so we're going to take what's the stuff, what is its derivative, we're going to let u equal the stuff, du is going to be the derivative of the stuff, we're going to do a substitution so that all of the original variables become u, we're going to integrate that easier problem, and then we'll stick the original variables back in, and that's how we're going to solve it. Okay, so the hardest part is what's my u and what's my du. If you can figure out those 2 things, then it's going to become a much easier process. But we have to think about what is stuck and let u equal that stuff that is stuck. Okay, let's look at our first example. It says use substitution to find the antiderivative of this stuff. Okay. To do this problem, back in the day, think about what we did for derivatives. If you look at that and go, hey, for me to do the derivative, I have to do the chain rule, right? That fourth power, we would have to do 3x squared plus 4 to the fourth power in order to just do like our power rules. Otherwise, we got to do the chain rule. So if you think about that in the light of a chain rule, our stuff that is stuck is 3x squared plus 4. That's what we're going to make our u equal to. Now, we're going to take the derivative of that. The derivative should be living in the problem somewhere, okay? So the derivative of that in terms of x is 6x. Now, we're just talking derivatives. The derivative of 3x squared is 6x. We see a 6x dx in the problem, okay? So we already know that this is going to be a u. Now we need every other x to go away. So we have to think, what is 6x dx? Well, du is exactly 6x dx. Just cross multiply that over. So we know that that is a u inside of a fourth power. This is equal to du. So let's do our substitution. So we get a u to the fourth. This stuff is equal to a du, so we stick a du on. Now, at this point, we have identified what the stuff was that was stuck. We made it a u, we made it a du, we've substituted in. So we've done the first 3 steps of the process. Step 4 is just forget about the original, forget about everything that's there, and just integrate the nice, easy problem you have created. To integrate u to the fourth, remember it just becomes u to the fifth over 5 plus c. Now the last step is to put the u's back in. Or I'm sorry, put what u is equal to back in terms of x. So remember what we know. U is equal to 3x squared plus 4. So that's going to go right here. So we're going to have 3x squared plus 4 to the fifth power over 5 plus c is our final answer. So we use our u substitution to create an easier problem that we're going to integrate, and then we stick the original x's back in. That's it. That's u substitution. Du goes away when we integrate. It's the process of that. Remember the original definition of an integration, that was the base triangles. When we do the actual integration, those are accounted for. Okay. Now, from here, let's do a little check if we were right. The derivative of an integral is the function inside. So if we take the derivative of that, we better get the function we see up at the top inside. Okay. So what would we do? Well, we would drop the 5 down in front. Stuff would stay there. We would multiply by the derivative of the inside. Is that, if we simplify it, the function that was inside of our original stuff? Well, it sure is. It's, oh, I'm sorry, the power goes down by 1. Boop. Is that the function that we see inside of Mrs. Saw did it right? Yes, it is. So what do we get? The 5's go away. We have a 6x. You're not going to see the dx when you do that differentiation, but you should see that 3x squared plus 4 to the fourth, 6x. We see a 3x squared plus 4 to the fourth times a 6x. Okay, so you can check your answer to an integral by doing a derivative. You better get the function inside. So the answer to our problem, if you take its derivative using our rules of derivatives, you better get the function inside. And these always will require a chain rule, or you did something funky. Okay, These are always going to require a chain rule. Any questions about this example? Do we have any questions? Okay, let's do another one. What is the stuff that's stuck inside? What is the stuff that's stuck inside? Yep, the z squared minus 5. Is its derivative or a multiple of its derivative living on the outside? Yes, a derivative of z squared is z squared minus 5 is a 2z. There's a multiple of that living on the outside right here. So let's do our substitution. So our u is going to equal the stuff stuck inside. Du is going to be, du dx is going to be 2z. And now here is where you have to fix the problem that there isn't a 2. In the problem, there is only a z and a dz. So we need to rearrange this so that one side says z dz, the other side says everything else. So the 2 needs to go over here. Oh, I'm sorry, and this would not be dx. That would be dz. And that the dz goes on the other side. So we're going to divide by 2, and we are going to cross multiply by our dz. So now let's look back in our problem. This is in our problem exactly. Z dz is in the problem. It is equivalent to 1/2 du. This is in our problem. It's going to become au. Now think about when we go to integrate this, we are going to want to write this as u to the 1/2 power. Now remember, z dz is equal to 1/2 du. So we have to put a 1/2 and a du. The way that I take care of it so that I don't make my mistakes when it comes to integration, I write the 1/2 in the front as a constant. I put the du in the back. And now I'm just going to integrate it. So just leave the 1/2 there. Our power is going to go up by 1. I'm going to divide by that new power. To divide by a fraction, just multiply by its reciprocal. Don't forget your plus c because there are no boundaries. Let's reduce that fraction. 1/2 times 2/3, the 2's cancel. So make that as pretty as possible with u's. And now we are going to put this back in. So that's what our u is going to be equal to in parentheses. We get the z squared minus 5 in the parenthesis that's to the 3/2 power. Well, how could we check it? We could do the derivative. 3/2 would drop down in front, multiply by 1/3, get a 1/2. Times the derivative, the inside would be a 2z, would be on the outside of that 1/2 power. Everything matches perfectly if we check our derivative. So we could do the derivative of that. We would get that. It's a perfect match. We know we're good. But if there isn't a 2 in your problem, you have to take it off by using a 1/2 to counteract that. So that one was a touch harder because our z dz wasn't a perfect match. Any questions about that one? Okay, let's keep going. Now, think about rewrites for just a moment. Remember how we didn't really like using the quotient rule if we didn't have to. So I'm going to rewrite this as the sine of t times the cosine of t to a -3rd power. Now I knew to do that because, I mean, I've had a lot of experience with that problem. You might not, that might not have occurred to you, but here's why I also did that. What's the derivative of the stuff that is stuck? Negative sign. Isn't a multiple of that laying it in the problem? So that's another reason I did that. This is my stuff. this is my derivative of the stuff, or super close to it. It has to be a multiple of it. Might not be exactly it, but it's going to be a multiple of it. So that I make U my stuff, in this case, a cosine of t. The stuff that is stuck, and the derivative should be hanging out in the problem. Now we're going to take the derivative in terms of t. The derivative of a cosine is a negative sine. Now let's go back into our problem and see what we have to substitute. One side of our equation has to say sine of t dt. This negative can't be there, so the negative is going to go on the other side. So put the negative on the other side with the du, leave the sine of t with the dt, because that's the exact substitution we want in the problem. We want a sine of t dt in the problem. Okay, so let's put our u in. It's going to go right there where our stuff is. So it is going to be a u to the negative 3. We found out that sine of t dt is equal to negative du. So put the negative out in front, put the du in the back. Any constant, put it out front, even if it's a negative. And the du goes in the back. Now we pretend that that's our problem. We're going to integrate that. You guys had tended to do weird things with negatives. When the power goes up by 1, your negative goes down. Do you understand? So your negative 3 becomes a negative 2. The negative is going to hang out in front, but we do have to divide by that new power. Okay, so remember what happened. Power goes up by 1. That's why it became negative 3 plus 1 is negative 2. Divide by that new power. Simplify it as much as you can before you put the c back in, or I mean the cosine of t back in. You could also have written it like this. That's also acceptable. One way or the other, let's stick our u back in. Remember, our u is equal to the cosine of t. So our final answer, you could either write the cosine of t to the negative 2 over 2 plus c. That's one option. Or you could write it 1 over 2 cosine squared of t plus c. Either way is acceptable. It doesn't matter to me. So you might recognize for this section, you have to remember clearly how to take a derivative and how to take an antiderivative, because you do both in the process. So derivatives, you remember all those rules. Antiderivatives, those rules have to go backwards. Everybody good with how I got the answer for that one? There is a way to do this problem using a tangent, but anyway, tangent and secant squared's hiding in that problem. Okay, let's do this one. I'm going to do a little rewrite. Before I do the problem. Now, this one has a unique thing I believe that's going to happen, but I'll show you what to do when this happens. We can't distribute the x in. That's what makes this problem have issues, that we can't do the antiderivative correctly. So we're going to let u equal the inside stuff. We're going to differentiate in terms of x. Is there a 1 in a problem? You can find a multiple of 1 anytime in a problem. So we just have a direct substitution that du equals dx. So let's think about what we got. This is going to be du. This is going to be u. We still got an x sitting there, don't we? So what the heck is x? Well, let's take this right here and solve it for x. Let's figure out what is x in relationship to u. Wouldn't you agree that u plus 1 is equal to x? So we can make that u plus 1. So now let's take out everything we've got and make them all u's, okay? So we get, in parentheses, u plus 1. In parentheses, u to the negative 1/2, and then du. We still don't have it very nice to take an antiderivative. But because this is one term, what happens with these problems, the original one you couldn't distribute. The new one does allow us to distribute, so then we can use our rules. And so we get a u to the 1/2 plus a u to the negative 1/2 du. And now it's just a power rule. We can take the antiderivatives of each piece without a problem. So u to the 1/2, let me remind you how it goes up by 1. So it is a 3/2 times its reciprocal 2/3. When this one goes up to 1, it's going to be 1/2 multiplied by its reciprocal of 2. Because there's no boundaries, put that plus c as kind of a little placeholder for our constant that could have been there. And now remember, once you've done the antiderivative, it's as simplified as much as I possibly can go. I can't do a darn thing else. Now we are going to stick the u back in. Every place we see u, we're going to replace it in parentheses with x minus 1. So our final answer would be 2/3 x minus 1 to the 3/2 plus 2 times x minus 1 to the 1/2 plus c. So remember, our rules of antiderivatives are going to be there. If you can't do an antiderivative, ask yourself, would I have had to do a complicated rule, possibly a chain rule, to get this problem done? If that, what's stuck inside, make that your u. Every x in the problem has to go away and become u's. Do the antiderivative. On the final step, put the x's back in. Makes sense kind of a little bit? Okay. Let's do another one. Now, the only difference between what we have been doing in those 3 examples and this one, you'll notice there's boundaries. I'm going to show you how to do this problem 2 different ways, and this only works if there's boundaries. Excuse me. So we're going to ignore the boundaries for the first way I'm going to do it. We are going to see we've got that 1 plus 2x to the 3rd to the 5th power. That is not something that you would want to do the 5th power. You know, think about 5 of those parentheses and multiply all that out, and that's disgusting. So that tells me somewhere they probably did a chain rule. So I have to do U-substitution. So I'm going to let U equal the stuff inside. I'm going to take the derivative in terms of x, or whatever our variable happens to be, and I should get a multiple of what's in the problem. And I do. I don't have a 6x squared in the problem, but I do have a plain x squared in the problem. So I'm going to move the 6 into the other side and move the dx to the right and the 6 as a 1/6 on the left. So I'm going to do my substitution. I'm going to ignore the boundaries for now. So when I do my substitution, I get 1/6. I get u to the 5th du, okay? Because this became a u to the 5th. This became a 1/6 du, okay? Now I'm going to integrate. That's going to be 1/6 times u to the 6 over 6. I have boundaries on there. I don't really need the plus c. Let's put our x's back in, and then we'll write our boundaries. So it would be 1 plus 2x cubed to the 6th power over 36. And I'm going to plug in the boundaries from 1 to 0. So if I did it all the way like we've been doing in the past, did I do something funky? I'm sorry? Oh, gotcha. So remember what we do. We're going to let U be the stuff that's stuck. We have to find the derivative, but it's not just 6x squared like we want. It's an x squared, so move the 6 over. Now we substitute in. Now we do the antiderivative. Stick your x's back in. And now we are going to use our boundaries. So our boundaries are going to be, if we stick in 1, we get 3 to the 36 over 36, or 3 to the 6th over 36, minus 1 over 36. So 3 to the 6th is 729. So that's 729 over 36 minus 1 over 36, which is 728 over 36. That does, they are both divisible by 9. Are they both divisible by 9? No, they're both divisible by 4 for an answer of 182 over 9. Okay. Now that is one way to do it. But I'm going to show you a different way. Another alternative, let's say that we get all the way to this point. Okay. And we don't want to put the x's back in and see this. That looks disgusting. What can you do to fix it? Well, if x is equal to 1 and x is equal to 0, those are our original boundaries, then u is equal to 3 if I stick in 1 right here. And if I stick in 0 right here, I get that u is equal to 1. So what you can do is you can change your boundaries and never use x's again. This is the boundaries from 1 to 3. Well, if we change our boundaries to be u's, because our original boundaries were x's, now our new boundaries are u's, guess what we get? We get 729 over 36 minus 1 over 36, which is 728 over 36, or 182 over 9. So you get the exact same result. So what you can do is you can change everything, even the boundaries, into u's and never have to touch the x's again. It's up to you if you want to do that. You still end up kind of doing the same math one way or the other. So if you change the boundaries and make everything from the beginning of the problem u's, you're okay to do that. But you have to change even the boundaries to u's. Because if I stick in 0 and 1 into this, I get a totally different answer. I get 1 over 36, which is totally wrong. Okay, so you have to be careful. If you want to use u's from beginning to end, you can, but change your boundaries to match. Okay. Oh yeah, sure. So again, I'm doing the problem both ways. You don't have to do it, you know, pick away, but good. Okay. Let's do this one. You may recall, let's think about e's. We did e's very quickly when we were doing derivatives. The derivative of e to the x was e to the x. Okay. Now let's remember what the derivative of e to a function of x was. We had to use the chain rule. We left it alone, but then we multiplied by the derivative of the stuff. So when you see an E set in the problem, this is most likely the U we get to use. The power itself will usually be our U, and a multiple of that derivative is on the outside. What's the derivative of that? 8x. A multiple of 8x is on the outside of the problem. So when you see an E problem, just let the U equal the power. Most of the time, that's what's going to work for you. Okay. So we're going to let the U equal that power. Now let's do the derivative. The derivative of that in terms of x is 8x. Think about what we have on the problem. We have an x, we have a dx, we don't have an 8. So that means we're going to take the 8 to the other side and the dx to the right, 8 to the left. So 1/8 du equals x dx. Now that's a perfect match as to what's in the problem. So now let's do our substitution. Now we have boundaries, so we can do the trick where we change the boundaries. I'll let you decide when we get to that point. Okay. So we get 1/8 e to the u du. Okay. This became a u. This became a 1/8 du. Everything is now used in the problems. Let's make the boundaries. Let's do it like that. Okay. So if x is equal to 1 and x is equal to 0, here's our equation for u, 4x squared plus 3. If we stick in 1, we get 7. So that's our upper boundary. If we stick in 0, we get 3. That's our lower boundary. We never have to deal with x's anymore. We're done with x's. We get to do the rest of the problem in terms of u's. Okay. The antiderivative of e to the u is e to the u. The 1/8 just hangs around for the ride. Stick your boundaries in, upper bound minus lower bound, and then we're done. So that would be 1/8 e to the 7th minus 1/8 e to the 3rd. I don't know what those are. I don't care what those are. That's like if there was a pi in the problem, just leave it. So that would be our answer. If they wanted something like where they wanted, if it was an application problem where we were dealing with a real life thing like a volume or something like that, then get a decimal. Otherwise, stop right there. That is our problem. Okay. So using our tricks to change the boundaries for our definite integrals are nice. You don't have to do that trick. Sometimes, especially when a problem like this, it is a very nice thing. Okay. So that, yes. This u is equal to 4x squared plus 3. So if x is equal to 1, that's where the 7 came from. And then if x is equal to 0, that's where the 3 came from. No, just plug those into what you made your u. Yeah, just plug those into, and that will change your boundaries. Otherwise, if you don't have boundaries, you do have to always stick those x's back in at the last step. Okay, and then here's your homework. So tonight, please, and even though you only have 5 minutes, do at least 2 or 3 of these. Work on some of these tonight. So I want you to come in tomorrow with questions. Hey, I don't understand number 7, number 10, number whatever. And we'll then go over questions. Well, 259. Anyway, and we'll go over some questions tomorrow, and then we're going to work on the practice tomorrow. This section is super important because it's difficult that you practice now, not in a week from now. And some of you have lots and lots of homework that are late. Get those things turned in to me, okay?